Welcome to week 4 of our advanced data analytics. As you see, there is a pretty promising term in the title. We call it the free lunch algorithm, which means, of course, not really free lunch. There is no such thing in information theory that you can get something from nothing. In this week, we will talk about several families of random algorithms. A common property of those algorithms is that they allows you to construct models in a way that you might not be able to imagine yourself by repeatedly doing doing experiments or model construction from randomly arranged data sets or configurations, and cleverly combine the models that have been built into the final or product model, which will explore the data in a way that has been automatically designed in the entire procedure of doing random experiments, model construction, and combination. So more specifically, our focus is Ensemble Methods, which is a methodology of constructing multiple predictors and to fuse the predictions by those predictors into a final conclusion so that statistically the final conclusion tends to be more accurate than the ones made by any individual predictor. The motivation behind the ensemble method is intuitive. The intuitive consultation to the wisdom of crowd to have superior predictor which is stabler. But if you read the words on this slide, it seems to not be explaining things too much. So let's take it this way. Ensemble method employs multiple random experiment so to reduce the model bias while does not incur excessive model variance by smartly build the models with complexity that is only affordable given the training data. Well, I know that sounds mouthful. Let us have a look at perhaps the simplest example of an ensemble. Suppose that we have predictors which making a committee. Let us say we have 3 predictors. Call them Alice, Bob, and Charlie. They both are trying to make a prediction of some situations, such as whether is it to be rainy or sunny tomorrow. Say each of our committee members, Alex, Bob, and Charlie, they have the individual accuracy about be 60%. And when we make our final prediction, we take the majority vote. That is, we take if 2 out of 3 of the people predict in one way, we will take that way as our final prediction. And let us have a look how this committee will perform compared to individual predictions. This table lists all the possibilities of making predictions by Alice, Bob, and Charlie. See, for example, the probability of Alice making a wrong prediction is 0.4, and for Bob to make another wrong prediction is 0.4, and for Charlie to make a wrong prediction is also 0.4. That means all 3 of them are wrong. And of course, in this case, the ensemble will arrive on a wrong conclusion, but the probability of this will be 0.4 times 0.4 and times 0.4, which is about 6%, quite small. And have a look at another situation. In this situation, Alice is making a correct prediction that happens with a probability 0.6. And here, Bob predicts correctly with a probability 0.6. And Charlie predicts wrong and with a prediction of 0.4. But the ensemble will tolerate the wrong prediction by Charlie in this case and arrive a correct prediction. The probability of such a situation happening is 0.6 times 0.6 times 0.4, which is about 14%. If we carefully list all those possibilities in the table and calculate according to whether the ensemble arrives to wrong or correct predictions, summing the different probability of different situations together, we'll have a number of the ensemble getting the right or wrong decision. In this case, ensemble has something like 65% chance of being correct. That is nearly 5% gain compared to the individual prediction's accuracy. I make this table. I think we can change this number so to have a look on different situations how the predictors perform. Like we can change this into 0.8. In this case, well, the chances of getting a correct prediction by the ensemble increase to 89, nearly 90%, and the gain also increases. Previously, when the individual predictor has the accuracy of 0.6, the gain is about 5%, and now the gain is 89.6% against 80%, and we have an accuracy gain of 9.6%. Another intuition is, of course, we would like to see another probability of what if we employ more committee members in the committee and say if a larger crowd let a larger crowd vote, we can have more accuracy. The answer is yes. Let us get our hands dirty and have a look at this simple example. We create a function, let's call it evaluate and visualize the performance and the committee. This function accepts the prediction accuracy of a single member of the committee and how many people in the committee. And the last parameter is a switch. By default, it is true. That is, we will draw each committee's prediction. I'm sorry, this parameter is not the number of a committee, but theories of numbers of committees of different sizes, such as if you give this number a value such as 1, 3, and 5, this function will evaluate a committee consists of a single member 3 members as our previous example for Alice, Bob, and Charlie, and 5 members. So let's have a look at the construction of this function. At the beginning, we allocate an empty, sorry about the noise, we allocate an empty list. In this list, we will store the record of whether the prediction of different sizes of the committees is correct. Now, for each of the committee, we use this temporary variable to loop over all possible committee sizes and give some initial correct predictions. This represents the correctness of individual committee members. Okay, we do not need to explicitly record individual predictions, but we want to know how many predictions are correct and how many are wrong. For each member in the committee, in this particular committee, such as if you have a committee size of 3, here we will have a range of 3. Okay, that is, we will have a member of the first member, second member, third member, so on and so forth. Here is the K representation of the random event. Okay, now look, the essence of this this programming is we have this random event to be sampled from a random generator. If you remember it, well, this RNG is a random generator which we allocate at the beginning of this definition. This doesn't matter. You can use other generators, but the important part is you have to have some mechanism to draw a random number uniformly from 0 to 1. If we can draw a uniform random number in this range, and consider that, for example, if this P probability of a single prediction to be accurate to be 0.6, then if you have a number uniformly distributed between 0 and 1, the chance for this random number to be less than 0.6 is exactly 0.6. So stochastically viewing this event, it will be equivalent to the other event. That is, this particular committee member is making a correct prediction. Note this transformation in the semantic sense. We use the event of a random number less than some threshold to represent another random event that is member is making a correct prediction. As long as these two events have exactly the same probability of happening, we can use one event to represent the other in our calculation of the probabilities. So, stochastically speaking, they are equivalent, although semantically they are quite apart from each other. This is the essence of many random algorithms. Keep this in mind. Okay. So now we have an event representing that the member is making a correct prediction. So of course, if the prediction is correct, we would increase the number of correct predictions. Okay. After this loop, that means each single member of the committee has made its prediction, her prediction. We compare the number of correct predictions with half the size of the committee. If it is larger than half the size of the committee, we see that this committee is making a correct prediction. Otherwise, we think the prediction of this committee is wrong. So we can append 1 or 0, 1 represents correct and 0 represent incorrect to this list. Okay, this part of the code is that the function of this part of the code is that after assessing the correctness of each of the committee, let us draw whether the committee has making a correct prediction against the number of members in each of those committees. This bar function is another data visualization functionality provided by matplotlib. This parameter represents on which positions I would like to draw a bar, and this parameter represents the height of the bar. So the meaning of this statement is that at each committee size, that is on the x-axis, we draw the bar on positions like 1, 3, 5, 7, so on and so forth. And at those positions, we draw a bar of height 0 if the committee of that size making a wrong prediction, and draw a bar of height 1 if it is making a correct prediction. So that will intuitively showing us, displays us how the performance of committees of different sizes. And we let the function return us the assessment of each different sizes of committees. Okay, let us, for example, run this cell, and in the following cell, okay, do a single experiment first. Run this. Okay, have a look. Which means for a committee size of 1, it's making a correct prediction, and for 3, well, interestingly, it is making a wrong prediction, so on and so forth. You will see correct predictions at positions where there is a blue bar, and incorrect predictions where there is some void. But we can expect, for example, if we run this function again, probably we'll have a different result. Why? Think about that for 3 seconds, perhaps. Okay, because the algorithm is random. All of the committee members, whether for all the committee members, whether they are making a correct prediction is a random event. In the particular case, for this p single, that random event has a chance of 0.6 from happening, and if we run this algorithm again, the assessment of each committee may change. Let's have a look. Well, that is different from the previous one. So originally I'd like to do it multiple times to have a more accurate impression. So they're different. Okay. So, and also in the next step, we may, for example, do the entire operation multiple times, many times. And for example, this number is a little bit too big, smaller one. I allocate an empty list here and do 1,000 experiments. For each of the 1,000 experiments, we evaluate a number of committees. So, oh yes, and record the outcome of each experiment. Afterwards, we will arrive at a two-dimensional array. Each row of the array consists of 0, 1 prediction correctness of different number, different size of committees of this experiment. That is each row. Let's have a look. Let's print its first 5 rows, and for each row, print its first 10. That's 8. The 8 elements. So that is it. Each row represents one round of experiment, and each element of the row represents a committee of different size. That means in the first experiment, a committee of a single member make a correct prediction, a committee of 3 members make correct prediction, a committee of 5 members making a wrong prediction, so on and so forth. Now, if we take the average of different experiments, that is taking an average of this matrix along this direction, along the row direction, we would arrive the average accuracy of different sizes of committees. Let's do this. Say mean the zeroth axis means the axis of this direction, and this is the axis equals 1. And if you have a third dimension, say if it is going into the screen, that would be axis equals 2. So let's calculate this quantity, and we can plot it. Give it a little bit information, x level to be committee sizes, let y level to be better. So that is the motivation of employing a committee or ensemble. But wait, we may ask a question. During all the calculations, we consider that when one committee member making a decision, the correctness of that committee member is independent, is not affected by other committee members. But what if, when the committee is making its decision, something happened behind the closed door? For example, in the very simple 3-member committee, Alex, Bob, and Charlie, how about if Charlie simply follow Alice, and then Alice's decision will single-handedly dominate the current committee, and Bob's opinion does not count. So there must be some conditions to meet for a committee to run normally as expected to improve the prediction accuracy. And if we view the problem from another aspect, is that we may find this is quite different from what we will expect of some algorithms that learn something from data. So, plainly put, that is not learning. We haven't seen any observations, and we arrived the predictions directly, happily assuming that we have some committee members that can make predictions independently, somewhat correctly for us, and the only thing we are worrying about is to summarize their votes and get final conclusion. But where are their predictions come in the first place? The answers to the above two questions. First, how to find individual committee members, the predictors, so that when they run together, we can form a normally functioning committee. And secondly, how to link the idea of using a committee of predictors, link this idea to our main scheme of learning from data. The answers are connected. So the individual predictors in practice are not manna from heaven. We need to create them ourselves. And to guarantee their independence with each other, we need to invent smartly schemes so that each of the predictor see different aspects of the training data. There are multiple ways for the individual predictor to see different aspects. That is the meaning of different aspects has different aspects, such as they can see different subsamples of an entire training sample, or they can see different subsets of the data attributes, or otherwise, like both take subsamples and subsets of samples and subsets of the attributes. And secondly, we need these individual predictors are predictors at all. For example, they need to perform a little bit better than random guess. But generally, this won't be an issue as long as you provide the predictor some information from the data, as long as the information is more or less connected to the target value we want to predict. A predictor utilizes that information will give them at least a hint of the target value. This is especially true when for a very common big class of problems of binary predictions. If the prediction is binary, as long as the predictor has some prediction that is a little bit different from half correct and half wrong, we can use that predictor. If, for example, a predictor has an accuracy of 30% for a binary classification problem, how can we use a predictor? Well, we can just simply flip its prediction. We will arrive at a 70% accuracy, accurate predictor. So there are two requirements of the individual predictors we can use to make an ensemble or committee. That is, first, they must to be some predictors, provide some information about the target value, and this requirement is generally easy to meet. And secondly, all those predictors need to look at different aspects of the data so that their predictions are as much independent with each other as possible. This is much more difficult to achieve in practical data analytics. In the following discussion, we will look at a few different schemes that allow us to explore different aspects of the data. Especially, we will introduce very effective, very efficient, and commonly used algorithm called ADA Boost.